Okay, let's look at some problems here where you have to find the expected value of a random variable. So example 1 says, suppose 2 coins are tossed and we want to observe the number of heads that occur. Okay, so what I'm going to do here, since I'm going to observe the number of heads, I want to find the expected number of heads to occur if we do this experiment a large number of times. So what we're going to do is we're going to let x represent the number of heads that occur on any given trial. And so you could, if you toss 2 coins, you could get no heads, 1 head, or 2 head. So we're going to set up the table and we put all the possible x values in one row. Some books do this as columns instead of rows. It doesn't really matter. But the first row is going to represent the possible x values 0, 1, and 2, and the second row is going to represent their probabilities. Okay, let's look at the sample space. The probability of getting 0 heads would be 1 out of 4. There's 4 possibilities. The probability of getting 1 head would be, here's 1 and here's 1, so that's 2 out of 4. Okay, and then the probability of getting 2 heads would be 1 out of 4. Okay, so that's the probability distribution. And once you have the probability distribution table filled out, all you do is multiply each x value by its probability. So I take 0 times a fourth, I take 1 times 2/4, or a half, and then I take 2 times a fourth. And I add those 3 products together. And when you add these 3 products together, you're going to get 1. And that sort of makes sense because if you toss 2 coins, it kind of makes sense that you would average getting 1 head per toss. But remember, before the average, you might toss them 5 times and get all heads. But the idea is that if the coins are fair coins, then if you toss them maybe 100 times, you would get closer to getting 100 heads, because 100 heads would be an average of 1 head per trial if you tossed them 100 times. Let's say 3 cards are selected from a deck, and we want to observe the number of face cards that occur. Well, so I'm going to let x represent the number of face cards that occur, and I'm going to find the expected value of x. Now, if you draw 3 cards from a deck, you can have no face card, 1 face card, 2 face card, or 3 face cards. So let's find the probability of this occurring. So the probability of getting no face cards would be out of 12 face cards, choose none, and out of 40 non-face cards, choose 3, out of 52, choose 3 3-card hands. And so calculate this on a calculator, you get 0.4471. Probability of getting 1 face card would be out of 12 face cards, choose 1, 40 non-face cards, choose 2, out of 52, choose 3, which is 0.4235. And then the probability of getting 2 face cards would be out of 12, choose 2, times 40, choose 1, over 52, choose 3. And that's 0.1195. And then finally, the probability of 3 face cards is 12, choose 3, times 40, choose 0, over 52, choose 3. I had a little math error here I had to correct. So this is actually 0.01, not 0.001. Now, we know that the possible x values are 0, 1, 2, and 3. And from up here, we get the corresponding probabilities. So, we just put 0.4471 here, 0.4235 here, 0.1195 here, and 0.01. And then we just multiply them like we did before. 0 times 0.4471, 1 times 0.4235, 2 times 0.1195, 2 times, and then 3 times 0.01, and add those all together, and we get 0.6925. Now, so we're gonna average about 0.7 face cards per trial. Now, to make this seem more realistic, let's say that you did this experiment 100 trials. So let's say you did 100 trials, and let's say you got, I don't know, 65 face cards total. Well, then in actuality, you're getting 65 face cards per trial, per 100 trials. So you're averaging 0.65 face cards per trial, which actually is pretty close to what you expect. Where you would have a problem is if you expected to average 0.69 face cards per trial like we do here, and you did this experiment 100 times and only got 30 face cards out of 100 trials, because now your actual number deviates quite a bit, because now you're averaging only 0.3 face cards per trial. So in that situation, you would probably suspect that something was wrong with the deck of cards. So maybe somebody's giving you a loaded deck or something. Now let's suppose two four-sided die are rolled and we wish to observe their sum. So we're going to let X represent the possible sum of the die. Now since they're four-sided die, we can roll 1, 1 up to 4, 4. So the lowest sum can be 2 and the highest sum could be 8. And there's a total of 16 possible rolls. So let's talk about how we could get a sum of 2. Well, there's only one way we can get a sum of 2, and that's to roll a 1, 1. So the probability of sum of 2 would be 1 out of 16. You might want to write all the possible rolls out to see this. To get a sum of 3, there's two ways, a 1, 2 or a 2, 1. So the probability of rolling a sum of 3 would be 2 out of 16, or 1, 8. A sum of 4, there's three ways that you can do that, 1, 3, 3, 1, or 2, 2. So that's 3 out of 16. And sum of 5 is, there's 4 ways that can happen, 1, 4, 4, 1, 3, 2, or 2, 3. So, and so forth. And you can do the rest of these. The probability of getting a sum of 6, that probability is 3/16. Getting a sum of 7, the probability is 2/16. Sum of 8 is 1/16. Well, then you put the possible values of X, 2 through 8, in the table. You put the corresponding probabilities below them, and then you just multiply each pair, each column of the table together, and then add them all up. Now notice when I multiply each of these together and then add them up, I get 80 over 16, which is 5. I kept them all as 16, so I would have a common denominator. So I get 5. So the average sum in the long term, if we did this experiment a bunch of times, we would expect to average a 5. So just to give you a sample, let's say you did this experiment 10 times, and let's say that the sum of the dice after 10 rolls was 47. Well, then basically you were getting a total of 47 out of 10 rolls. So that would be, if you divide 10 into 47, you get 4.7, which is, close to 5. So that's not too far off. But again, if you were way off, if you were really far off from 5, then you might be concerned about the fairness of the die. Here's an example. This is more like a quality control problem. Suppose we take a sample of 2 light bulbs, so we're going to take a sample of 2, and we have 8 bulbs, and in those 8 bulbs we have 3 defective. So that means we have 3 bad bulbs and 5 good bulbs. It says, what is the expected number of defective bulbs? Well, since I'm asking for the expected number of defective bulbs, then X needs to be the random variable associated with the number of effective bulbs. Well, you're only taking a sample of 2. So you can't have more than 2 bad bulbs. So obviously you can get no bad bulb, you can get 1 bad bulb, or you can get 2 bad bulb in your sample. Okay? Now, so the probability of no bad bulbs would be out of the 3 bad bulbs, choose none, and out of the 5 good bulbs, choose 2. And then divided by 8, choose 2. That's the total number of samples you could get, is 8, choose 2. That came out to 0.3571. 1 bad bulb would be 3 choose 1 times 5 choose 1 out of 8 choose 2. That's 0.5357. And then 2 bad bulbs would be 3 choose 2 and 5 choose none, or 8 choose 2. So that's 0.1071. So I put it in my distribution table here, and then I multiply each pair together and add them up, and I got 0.75. So in that case, we expect to average 0.75 bad bulbs. Now I can't really go into it here because it's a little more complicated, but what happens there is this is a way to do some quality control in manufacturing, because you can determine what your tolerance level is on the number of bad bulbs to expect, and then if you start taking samples and get more bad bulbs than you're expecting, then you can determine whether or not you can improve that. Maybe some machinery's gone bad, or maybe your employees have gone bad. I'll let you freeze the video and just read this one. This is just an interesting one where it's a lotto problem, like if you played Texas Lotto. Basically, what I want to do here is find the expected number of matches that someone's supposed to have. So this will tell you the average number of matches on a Texas Lotto ticket. Now basically, I won't go through the probabilities, but I found the probability of no matches, the probability of getting one match, the probability of getting two match, three match, four match, five matches, and six matches. And I put them in the table here, and then when I multiply each value by its probability and add them together, I got 0.667. So basically what that tells you is that the average person that buys a lotto ticket in this game is going to match less than one number, which is interesting because you have to match three numbers to even make a profit. Alright, there are some game examples that you can look at. Let me just summarize this game here. This is just a lottery, and let me just show you. Here we're going to let X represent the possible payoffs. Now, since you're buying the ticket, you could lose $5. If you don't win anything, you lose $5. If you win the $50 prize, you actually only get a payoff of $45 because you paid $5 to play. If you win the $100 prize, you only win $95 because you paid $5 to play, and the same thing for the $200 prize, you would only win $195. Well, if you look up here, there's 983 losers. So the probability that you lose $5 is 0.983. There's 10 winners for the $50, which would be $45. So there's a 0.01 chance that you're going to net $45. For the $100 prize, which nets you $95, there's a 0.005 probability, so you put that down here with the 95. And then for the $195, the probability is 2 out of 1,000, 0.002. And then if you multiply each of these together and add them up, you'll see that your expected value is $3.60 in the negative. So that means that the average person is going to lose $3.60. Freeze the video here and view this quality control problem. It's very much like the light bulb problem I did a minute ago. Okay? Freeze the video and read this one, and let me summarize it. We're going to let the random variable be the net gain per concert. So in this concert, you're either going to lose $12,000 or you're going to gain $20,000. If it rains, you're going to lose $12,000, and there's a 40% chance of rain. If it doesn't rain, you're going to make $20,000, and there's a 60% chance it doesn't rain. So if you multiply these two together and then multiply these two together and add them up, your expected payoff is $7,200. But remember, that's only in the long run. I mean, if you did just one or two concerts, you might lose money, but if you did 100 of these concerts under these conditions, then you would be expected to make $7,200 per concert. I'm going to leave you with just a couple of problems to let you read. So pause the video and read this problem here on the expected value of a game that I just made up. And notice that the expected value of this game is negative 17 cents. And then read this one. Pause the video and read this one, and then that's pretty much the end of the lecture on expected value.